how do we know that there are infinitely many prime numbers? We know that there are infinitely many numbers, natural numbers, counting numbers, because if somebody comes along and says, I've reached the largest number that can exist, you can say, okay, what number is it? And they'll tell you, oh, it's n. It could be which is an arbitrary number. And then you can say, but what about n plus 1? And consequently, they will say, well, okay, yes, then it must be the possible that there's a larger number. And you can apply that rule indefinitely. There's always going to be a larger natural number. But what about prime numbers? They become less and less frequent the higher that you count up the natural numbers. So you could say, well, eventually they'll stop. There'll be no more prime numbers to be found. Or you could say, well, no, that they will continue. They'll just be further and further spaced out. But whatever your opinion about it, it's pretty irrelevant, because what you need to do in maths is prove one way or another what the truth of the matter is. And there's a really elegant proof for this, which is Euclid's proof of infinite primes, which is to state that if you imagine that you found a prime number and you're contesting that prime number is the largest prime number that there will ever be, you can call that prime n, so p with a little n. And let's say that you believe that that's the largest number that there can ever be. There can be no larger numbers than prime n. Now, if I say to you, okay, then let's list all the prime numbers: prime 1, p1, the next prime, prime 2, p2, the next prime 3, prime 3. We'll put them all in order, and the list goes all the way up to your prime n, which you say is the largest prime number that can exist. And I say, okay, let's take all those numbers, let's multiply them together. Let's take all of those numbers. Then we end up with a very, very large number, and that number is divisible by all of the prime numbers, and therefore also by all of the compound numbers, because the compound numbers are always a combination of primes. Now, I'm going to add 1 to that very large prime number, and I'm going to get a new number. We call this number x. Now, that number is not divisible by any of the prime numbers in the list, and nor is it divisible by any of the compound numbers, because if it can't be divided by a prime number, it also can't be divided by a compound, which is itself a compound of other primes. So that number now that I've come up with, my number x, may or may not be a prime. If it is a prime number, then I've already I've proven my point, there's a larger prime number. But in fact, it's very unlikely to be a prime number. It's overwhelmingly unlikely to be a prime number. So we'll say that it probably isn't a prime number. If it isn't a prime number, then we know that it is a prime number which cannot be, it's a non-prime number which cannot be divided by any of the primes on your list. So by extension, there must exist a prime number which will be a divisor for x, which is larger than prime n. So that's the step of thinking which sometimes it's a bit hard to imagine. So I'll explain it again, perhaps more clearly. X is a super large number. Prime n is a relatively quite small number. Neither prime n nor prime 1, 2, 3, 4, 5, etc. can divide x. If x is not prime, it must have a prime divisor, because all numbers do. Therefore, the prime divisor must be greater than prime n and less than x. So I can't tell you what my larger prime is, but I can tell you for sure that there is one.